type of alternating current, which is referred to as a sinusoidal alternating current. There are two reasons that sinusoidal alternating currents are understanding them is so important. One is that when we make alternating current, and we make alternating current using generators, and in a generator there is a loop of wire which rotates, making that current a sinusoidal current. So history actually made sinusoidal current so important because this is how we discovered how to produce it. And then when we find out other sources of electricity, we have trouble, or we have to go into trouble how to convert it into sinusoidal current. Because, for example, now we are trying to use solar power, for example, to produce electricity. But the problem with solar power is that, or solar panels, is that it does not produce sinusoidal current. It produces really a constant current. So now, in order to use it together with all the other sources which we are having now, we should convert to sinusoidal and synchronize it with the generators. So one of the reasons is history. There is another reason, which is a mathematical reason. And it is that any periodic function, or in principle even not periodic function, if we, well, you haven't heard of that, they are referred to as Fourier series. So in Fourier series, a function can be represented, any function can be represented as a combination of trigonometric functions. Now, thing that we extend the period to infinity can be represented as a series of trigonometric functions. Now let's recall what series are in general. You are aware about certain series, power series, right? You can represent a function in terms of power series. What do we call these series? Taylor series, for example, or Maclaurin series. Right. Now, we can select some other functions to represent functions as series. And if we choose trigonometric functions, now those of you who are advanced in math maybe know what do we call these series. Series in which the terms are sine functions and cosine functions. What are they? All right. So, for a sinusoidal alternating current, both voltage across an element and the current through the element are sinusoidal functions of time. Now, doesn't it look like I'm redundant here? I'm saying that for a sinusoidal current, current is a sinusoidal function. Actually, well, let me bring a puzzle or question which a student asked me once, and it will clarify again that everything here is all right. The student asked me, what is more dangerous, current or voltage to a human body? What actually can kill, current or voltage? Well, think for a moment and we will vote. So who thinks that voltage kills? Who thinks that current kills? Why do you think that current kills? And I mean, without voltage, now, it is true, current kills. But now let me ask you, which current kills? The one in amperes Does current, which is expressed in amperes, kills? Who believes that? Who believes that another current kills? Ah, you have no opinion now. It's the other one. Current measured in amperes is as harmless as voltage. Voltage is an abstract concept. Current measured in amperes is an abstract concept. An abstract concept cannot do anything. It's the phenomenon current which kills. Yeah, so it's the other current. Yeah, the process, the moving charges are going to kill, not the rate at which they move. Therefore, also here, a sinusoidal alternating current, this is AC current. This is the flow of charged particles. The flow of charged particles, and if it is a sinusoidal flow of charged particles, voltages across elements and currents through those elements are going to be sinusoidal functions of time. I mean, it's not exactly true, because there are elements, we have elements for which they don't have be really sinusoidal function. They will maintain the same period, but won't be, like in a diode, for example, current is going to flow only one way, so we will have only half of the sinusoidal function. The most general form of a sinusoidal function is like that. So here I wrote function for the potential difference. There is a certain number here. There is a trigonometric function, a number, variable representing time, and a number. You cannot make it more general than that. And for sinusoidal alternating current, both quantities have the same form. Not only that they have the same form, but these two numbers are equal. This number in front of t in potential difference and in the current have the same value. Now, I want you to learn the names of all those numbers, because all those numbers have a name. The number which is in front of the trigonometric function is called the peak value of that quantity. So Vm is peak value of the potential difference. Im is the peak value of the current. And if we look at the plot, it is referred to as peak value because, well, the highest value which sine function can assume is 1. So if sine is 1, then potential difference is equal to peak value, or the quantity is equal to its peak value. So if we look at the plot, peak values are the highest values on the plot of the two electrical quantities. The argument of the sinusoidal function is called the phase of that electrical quantity. So omega t plus delta V is the phase of voltage. Omega t plus delta I is the phase of current. Omega is referred to as angular frequency of that current, and it is related, it is referred to as angular frequency because it is proportional to frequency. We just don't want to have a number 2 pi f, 2 pi times frequency, where frequency says how many oscillations occurs in a second. So f is a number of oscillations in a second. It is referred to as frequency. If we multiply this number by 2 pi, in principle it also reflects frequency, but in order to make a distinction from the frequency which says how many oscillations we have, we call it angular frequency, and the reason is just convenience, so that we don't have 2 pi in the formula. We have single number omega in that formula. But well, how about well, think about if why don't we imagine that this number is 0 and think that omega is 1? Oh no, let's make it 1 over, or just 2 pi. 2 pi. Think how many seconds does it take for the voltage to complete one oscillation. So at instant 0, sine of 0 would be 0. Right? Now after, let's say, half a second, well, let's make 1/4 of a second, we would have sine of pi over 2. Sine of pi over 2 is how much? 1, right? So, so the value changes to 1, to the highest value. Now let's take half a second. So we will have sine of pi. Sine of pi is how much? 0. It returned to 0, but it went just up and down back to 0. Let's take now 3/4 of a second. After 3/4, if I plug in 3/4 of a second, I will get -1, so it will drop below. And when I take 1 second, it will come back to 0. Right? So in 1 second, the voltage completed single oscillation. So frequency is 1 and angular frequency was 2 pi. All right. This angular frequency, if you look at the plot, says how much time does it take for an electrical quantity to complete an oscillation, which means to return to the same phase. Well, actually, I was kind of, because phase is measured with it's a number between 0 and 2 pi. So if it exceeds 2 pi, then we reduce it by 2 pi all the time. All right. Now the last number which we have is the delta, and the delta refers to as initial phase of that electrical quantity. Well, and again, like with initial velocity or initial position, it doesn't make much sense. Initial refers to the instant to which we assign time equal 0. So if we plug in time equals 0, then phase of that electrical quantity is going to be equal to the initial phase. And initial phase actually says, well, which way is the plot is shifted from a nice sinusoidal function. Now we can actually even figure out how about if we think about what is the phase, initial phase of the current, of the voltage, sorry. Is it positive, negative, or 0? Who votes that it's positive? Who thinks that it's negative? Who thinks that it's 0? Actually, it's positive. Yeah, at t equals 0, we have already a positive value of sine functions. Yes, so if this term is 0, sine is positive, which means that this number must be already positive, somewhere between 0 and pi over 2. For the current, initial phase is negative. Yeah, because we have that when we plug in 0, we got a negative value for sine function, which means that the argument of the sine function has to be a negative number.